Hello, everybody. Thanks for joining us today for the Learning Lab 21. I'm going to start sharing my screen. And that's going to be today's presentation. So I'm just going to turn off my camera so people can see full screen. So that's today's presentation. I'm going to be talking about the STEAM optimization in our Xeek competition. So just an introduction to who you are. So we are the Cruz Data Science Initiative, which is providing these learning labs. We are a branch inside Cruz that is focused on data science projects for geoscience data, energy, environmental, engineering, everything basically that's related to environmental and energy sector. We are doing projects for the academy and as well for the industry. We do programming training as well in Python, R, and MATLAB. That can be from starting programming ideas to create applications and machine learning applications. As well, we provided those learning labs. Those are free webinars that happen every 2 weeks. And they can be accessed, the old webinars, if you visit us in our website, cruz.org, or our YouTube channel. And those are the hosts for today. I'm Marcelo Guarido. I'm going to be the one presenting today. I'm a senior data scientist at Cruz and also the head of the Cruz Data Science Initiative. So Daniel, would you like to present yourself?
Yeah, my name is Daniel Trada. I'm an associate professor here in the University of Calgary in the Department of Geoscience, and I'm just helping Marcelo with this.
Thank you, Daniel. And Brian Russell. I think I misspelled your name, sorry.
Yeah, can you see me?
Yeah.
Okay. Yeah, I'm Brian Russell actually, we just got spun off. I'm no longer with CGG. I'm with GeoSoftware is the name of our new company. We used to be a division of CGG, but now we're an independent company. I'm also actually we've updated my thing there. It does say Vice President GeoSoftware. I'm also adjunct faculty with Cruz. I'm an adjunct professor at the University of Calgary in the geoscience department. And I've had a long interest in machine learning.
Thank you, Brian. And David Emery, he couldn't join us today, but he's a common presence in here. He's a geophysicist specialist, and he's now a PhD student at the University of Calgary, and also a very regular member of the Cruz Data Science Initiative. So what you're going to be talking today is about the Xeek competition named the STEAM Optimization and Other Oddities. This competition, it had the goal to provide us injection information, steam injection information, and oil production. We had to use this information and try to predict what is the remaining oil saturation in the reservoir. So kind of a very simple idea of the project. So they're going to provide us information from 400 wells, and you have to come with the best prediction. Those are all the features that, all the information they are giving to us that goes from the well identifier and all the other information like the remaining height of oil column, remaining height of gas column. So those are going to be very two important features that are coming from in this project. And the goal is to predict the percent decrease in oil saturation. So they wanted us to predict how much oil we removed there, basically. And this is a very interesting data set they provided to us. So basically it's a table, a spreadsheet that contains both numerical and categorical data. And it showed to be a very complex and challenging data set for us to work. So it has 400 wells with a non-negligible number of missing data, but we are not going to be working with missing data today. We are going to neglect them. They have variables. Most of the variables, they have low correlation with the target, besides 2 of them. And they have a combination of numerical and categorical features. So that make us to choose modeling and how to treat the data previous to the modeling a little bit differently. And that's what you're going to be focusing on today. You're going to be working on the exploratory data analysis. So the idea is to do data visualization, understand all the variables and what's happening there. Then we're going to do some machine learning modeling and some model evaluation and interpretation. One way to deal with these numerical and categorical features, one simple way is to use models that are tree-based, because as they are a combination of if conditions, so you can have a mix of numerical and categorical features. And what you're going to be using today, actually, is a gradient boosting, that is an ensemble of decision trees. And what it does, it's going to start with a tree that's going to be making your decision that can be used for classification or regression. And then it's going to start to fit over the residuals. And then you're going to have an ensemble of windows, one after the trees, one after the other. So basically, it's represented by a sum of trees. And in the end, usually we have a quite powerful model that can do regression or classification. This model, the gradient boosting, it's powerful, but it can get very slow to run, as it's very hard to parallelize, as one tree is dependent of the next tree, of the previous tree. So you cannot build those trees in a parallel way. And actually, there are different libraries and coding programming that you can do to run the gradient boosting and do modeling. So here are several examples from where we can use gradient boosting. We can use both in Python and R. So there are the scikit-learn that has their building for the machine learning and the gradient boosting. There are the XGBoost that is the one that you're going to be using today, but the one that was built in the Tidymodels in R. They have the LightGBM, the to recreate. So there are different libraries that can work on different programming languages. So what you're going to use is basically your decision. And basically that's this for the introduction, and that's the coding time. Okay, so that's the code in R that we're going to be making available for you after this learning lab. And what you're going to be making available for you is a folder that are going to contain all these data set in here. We're going to have the R project that's going to open your R Markdown. Sorry, where we have saved all the project information, like where are our folders that you're going to be using. You're going to be providing this R Markdown. That is this file that we open here. That's similar to a Jupyter Notebook. We have the coding chunks where we do our codings. That's equivalent to a coding cell in Python in Jupyter Notebook. And everything outside is going to be Markdown. So we can build a report. The only difference, it has a YAML header where you can do a bunch of changes and how you can export your code to. So in this case, you're going to be exporting to a HTML file, and that's going to be this file. If you export all this code to the HTML, you can actually have a report to present. So I'm just going to be opening just to show. And that's the same code that we have in R Markdown, but now as a report. So that's one of the advantages of using this type of languages, because you can do this and build a presentation straight from your code. The data that you're going to be using is from the competition, the Xeek competition. So I'm just gonna open their website in here. So that's the competition website. One of the first thing that they have announced here, that two variables that the one that you're going to be explaining today, why they removed it from the data set, basically because they are calculated from the target, and they're going to show during the coding and what happens. But they have all the challenge description, so they want us to use all the injection information and try to do the prediction of what is the well production over time. So they want to know by giving information of injection, how efficient is the removal of the oil. They have here the data set that you can download if you join the competition. They even have the submission sample, the train, and the test. So the train is the one that we have the target, and the test, we don't have the target. You just have to do the prediction in this data set and send the submission if you want to. So we can just send a submission. So for the data set that they provided, so they provide a submission sample, a test data, and a train data. And what you're going to be working today with this train.csv. So I'm just going to open. And that's the data they provide. So it's a simple table that we have. The first row is the number of the name of the column and the information that we have for different wells. So basically, this one would be a type of a well ID that has these numbers. So this one is one well, all the information from one well. And they have the sand, basically it's the area where they are doing the injection. So it's a different sand. And inside this well, they have those sands and the survey date. So for this first well, for this sand tools, D1, they did the survey or the measurements in two different dates, one in 2012 and one in 2016. For this other sand, the D2, they did three measurements, 1990, 2012, and 2016. And that is going to happen, this type of data, for all the other wells. So we have all this combination. And some of them, they have more, like this one, for this well. And this sand, they did the survey several times. They have the deep information. Let me just expand all the titles. They have the average oil saturation, original oil saturation, the original oil height. So those are the two features that were removed, but I still have the original data set. They have the total injection, total injection for the sand, for this specific sand, and some information that comes from the adjacent wells also. The total production, some linear distribution or distance from the production wells, and that's the target. So this is going to be a number from 0 to 1. We want to say what is the reduction of the oil saturation. So if it's 1, means that we removed all the oil. If it's 0, means that we still haven't removed anything. And then let's go to our coding. So this is our markdown. So I just do this first chunk just to say what I want to do for all the other chunks. So I just want to say that I don't want to do any warning message. And this is the quality of the figures that I'm going to be plotting. Here, I'm just uploading what are all our variables. So this is from a file. and it's in this figures folder. So it's just this file, and that's one way to upload this and to build our report. And then we are going to start by loading some libraries. And those are all the libraries that you're going to be using today to load the data, to do the data, exploratory analysis, exploratory data analysis, sorry, and all the plottings that you're going to be using, the machine learning, and also this reticulate is the one that we use to run Python inside R. We're just going to use this as an example. So as you're going to be using dates, so I'm going to be uploading this library lovely dates. The Tidyverse is the one for do data exploration and do all the data wrangling. So if you are used to Python, that's the equivalent of pandas. The scheme-R and data explorer is to do the exploratory data analysis. Plotly is to do interactive plots. TimeTK is to do plots of a time series, as well deal with time data. Tidyquant, I loaded twice. So basically, I'm just gonna put in the visualization. Tidyquant provides a bunch of other functionality, but they also create a nice theme for plotting. ggally is used to create pair plots, the correlation plot, and some of palettes. The Tidymodels for the modeling. The VIP is to calculate the feature importance, and reticulate for the path. So if you want to run, just Ctrl+Shift+Enter. So we're going to be loading all the library. And here is how we're going to be reading our data. I'm going to use this read underscore CSV and just getting the data. So if you just load the data like that, that's the table we get. We have our date that is a character, and all the others columns, they are mostly numeric. Probably just have the send that is also character. Yeah, so you have two columns that are characters. You can see in here. Actually, can you guys see the code, Daniel and Brian? Do I need to make it larger?
Yeah, that's okay.
Okay. So what this symbol is, it's called a pipe. It's just saying that the output of this code is going to be sent to the next function. So it's very similar to the pipe in Linux. So when I just select this and run this selection, I'm just making sure, even though it was loaded as a table, to make sure that it's loaded as a table. Table is a data frame in R. It's an evolution of the data frame in R. And here, what we are doing in this mutate, we are just making sure that the date is going to, instead of character, is going to be converted to date. So we can do calculations with dates. And I'm also creating this well ID, because instead of to be these numbers that start from 435 to start from 1. So it's going to be easier later on to get separate wells for tests. So I'm just making this to be from 1 to the last number. That's going to be 400. So when you run all this code, that's what we have now. So now the survey date is understood in R as a date column. And we created this new one, that's the well ID, that goes from 1 to 400. Here, I'm just ordering the data from the well ID, the send, and the date. I just want to make sure that all the dates are correct, that the oldest survey is first, because looking at the data, I saw that sometimes it was not the oldest one, the first for one send. So I'm just making sure that it's correct in time. And that's what you're doing here. And then I'm saving to this data table. And the next one, I'm just calculating the time difference between the surveys for each one of the wells, for each one of the sands. And it's gonna be the time difference in days. So this is from the Lubridate library, this time diff. And that's why we converted it to date before. It's gonna be easier to work with dates. So when you run this part, that's the new table that we have. Instead of having 21 columns, now we have 22, but we kept with 8,004 rows. And we created this new column. That's the time difference in days between surveys. So 0 means it was the first survey, and then when the next survey was done. So we have here that the next survey was done 8,333 days after the first one. Here, I'm just selecting what are the numeric columns, because you're going to be using these for plots. Basically, I'm just creating this vector. And if you run this, those are just the names of all numeric columns. And I'm just removing the well ID from this one. That's why I'm doing these selections. I'm removing the well IDs, the first one and the last one. And then I'm re-adding the time difference and this one. Here is just to understand the data, just do a summary of our data set. So this is from the library scheme R. So I just get our data and run this scheme. And that's what we're going to get. So it's going to say that we have 32 columns, 8,004 rows, 1 character column, 1 date column, 20 numerical columns. And then it's going to give the information from each one of those columns. From the character columns, it's going to say the min max of the size of the numbers, of the names, and how many different names we have, and how many white spaces, how many empties. We don't have any missing in this one. And it's giving this all this interesting information. The same for the date. It's going to give you the oldest and the youngest one. So the oldest survey is from 1990, and the newest one is from 2020. And we have 550 different dates. And this is for all the other numerical variables. So we have the number of missing. So we can see that we have a bunch of missing from these columns. The complete rate, basically how the percentage of the data that's complete, and all the other information like the mean, standard deviation, the percentiles, and even a small histogram with the data distribution. And there is this other one that you can do with Data Explorer. I'm not going to run this cell because it's going to take a couple minutes, but what it does is going to create for you a report. So when you run this, actually, it's going to create for you this folder down on the right side here named reports, and inside is going to create this file named the name that you gave in here. So you can create the directory that you want. Here we are selecting what is our target. So it's going to do a bunch of calculations here regarding to our target, and what is the title of the report. So when you open this in the web browser, so that's the file it's created. So it has a huge amount of information, all the number of columns, the missing information. So it starts to plot the percentage of discrete columns, continuous columns. If you have any column that is all missing, so no column is 100% missing. So the percentage of complete rows, that means that it has no NAs. and the total number of missing observations for the whole data set. It gives a data structure. We don't have any groups, so it's just all the columns are independent from each other. The missing data profile, so it's just a plot of the missing. So it's very nice for visualization and create reports. And you see that those variables here from the cumulative stem injection to the distance from the injection well 2, they have a nice amount of missing data, but it's still considered okay from this data explorer. And all the others are good, means that you have a good amount of data. They also do the univariate distribution, a better distribution of plots from these, all of the features. We also have this bar chart, these bar plots that are just how many times appear which one of those sands type. So instead of to do a distribution, because you don't have a continuous number, it's just do a frequency of each one of those type of sands. It's also doing a QQ plot. This type of plot is trying to see if the distribution is a normal distribution. So it uses on the x-axis what should be theoretical quantile, and here the true quantiles, and do these plots. So to be a normal distribution should be all fall over this straight line. So when you have those S's, all their different shapes, means that you don't have a normal distribution of this data set. That's quite important because in general, machine learning models, they assume that our data has a normal distribution. So if you do this plot and see that they have no normal distribution, so probably some kind of a transformation is required. They also do the QQ plot against the targets, so we can see if there is some kind of a high correlation, I guess. They also do the correlation analysis, so this one got a little hard to see. They also do the information from principal components analysis and how much of the variance was used, percentage of variance explained by each one of those components. We do this type of plots, and you have a bunch of this information that you can do and do your interpretations, basically. So it's very interesting to do this and build a very fast report for data analysis. But you don't need to create this report if you don't want to create this report. You can use some functions from this data explorer just to do the plots by yourself. So this one is just to plot the intro. That was the first plot that they showed. That was that one, the number of discrete columns. So you can do here by yourself. And that's nice because you can even change the theme. You can change what is the color of the background. You can do a bunch of different stuff in here. This is the plot for the missing. So what you noted that you have a bunch of missing data, but you're not going to worry about it today because the gradient boosting still can run with missing data. This one is from the GGLI to create a pairs plot. So what we are doing here, we are just doing a cross plot or between each one of those variables. And we want to see if you see at least visually some kind of a linear correlation between them. So the importance that you want to see, I know that those are small numbers and small names because you have a lot of variables for this plot, is this last row. So everything in this last row, the y-axis is the target, and you want to see for the x-axis that there are different features if you see some kind of correlation. And it's very clear that for those two plots in here, those are the remaining oil height and the remaining gas height, those are the two variables that are removed, that you have a very high correlation visually. And all the others doesn't seem to have that linear correlation. So what you're going to be plotting here, you're just going to be doing some correlation plots. The first one, you're going to be calculate a Pearson correlation. So the way we use this basic function from R just to create a correlation matrix. So if I just run this selection, what it does, it creates this correlation matrix. So the correlation of each variable is each variable. And then I just send it to this core plot from that library core plot to plot this. So we can do this plot and see how are the correlations. So the diagonal is 1 because it's the variable is itself. And you want to see some correlation. We can see, for example, the total production has a very high correlation with the total injection. What makes sense? And the total production, what is weird, it doesn't have that very high correlation with the remaining, with the target. That is the percentage of reduction in oil saturation. I would expect that a total production would have a higher correlation. But this is a linear correlation. Maybe the correlation is not linear. When you're calculating the Pearson correlation, that is the default from this function core, means that we are doing a calculated linear correlation. And what we see is that the remaining oil of gas has a high negative correlation, and the remaining gas height a very high correlation as well. So just try to see if there is some correlation that's not non-linear. The experiment can give some indication of non-linear correlation. So if you calculate the experiment correlations, that's the plot we have now. And actually, it increased a little bit the total production with the target. We have the total injection for this sand, also have a reasonable correlation, and increased the correlation of the other two. The gas height is 0.9 correlation to our target. So that's pointing that when you're going to do our modeling, this is going to be our most important feature, followed by the remaining oil height. So that's very important. When you are doing your machine learning project, first we have to work with your data, understand well your data, and kind of expect what are going to be the outcomes. So you can see that something is wrong or not when you're doing your modeling. Now here, you're just plotting some distributions. I'm just getting the well names and seeing how many wells we have in the data. We have 400 wells. And here, I'm just doing a plot that are going to be in the x-axis, the distribution, the difference, sorry, the time difference between surveys in days, and you want to see what is the distribution of that, the density, because I want to see how long usually they take to do the surveys. And that's very nice to use ggplot. This is an interactive plot because it talks very closely with ggplot. That it's the most common plotting tool in R. So I'm just going to explain how to build this plot. So we have our data table that we created. It's our data frame. And then you're going to send this to a ggplot frame. So we are just going to create here an empty frame. And we are saying what are the I statics, what are our X's, Y's, what is the color. So it's going to be colored by sand and fill by sand. So it means that you're going to be filling from the curve to 0. So if you run this, we are just going to, oops, I forgot to select this part. if you just run this. So we just create an empty canvas. So there is no plot yet. We just create, we just say that's ggplot that's going to be using this data and this information. So now we have to add what you wanted to plot. So we're going to be using a geo density. We're going to be doing a density plot. We're going to removing any NAs and do an alpha of 0.2, just the transparency. So when you plot that, so that's the plot we get. So this is a ggplot, but it's not interactive. Here we are just changing what are the name of the y-axis, the x-axis, the title for the title in here. Also, I don't want to give any names, any labs for the color or fill, so we're going to be removing the sand in here. And when you run this selection, also changing the background color, and also plotting, saying that the outside part is going to be transparent for when you're saving the image. So that's the plot we have. So we are going to save this to this P parameter. So that's a plot. And I forgot to select the P. And then we can just call this plotly and run P inside it. So we are going to convert this ggplot to a plotly object. And that's now our interactive plot, where you can see all the values in here, and you have the hover. And what I'm doing here, I'm just changing the legend after. I'm just saying now this is the way you run plotly. The ggplot is a plus. You're just adding things to the plot. For the plotly, you have to use the pipe. So the output of this, you're going to also include this. So I'm just going to say that the legend is going to be the horizontal, is going to be down here, the position, and then we're going to be giving a title. So it's going to be send ID. And one thing is that when I give you the zoom, you see that the x-axis didn't change. We don't see the numbers here anymore. So I'm just going to say that now I want to be tick mode auto and linear. So it's going to be also zooming the x-axis. So now running this. And then we have this final project or this final plot. So now I give the zoom and we see the days here. So for this plot, what we observed that most of the surveys, the difference time between them is around 21 weeks. And the second one, the second peak, is around 2 years and a half that they do the surveys. And then we have a high decrease, and then we have some surveys that took a very long. But most of the surveys we do until 1,500 days, basically. Here, I'm just going to be plotting all the distributions. So I'm creating all the plots for the distribution for density, if it's a continuous number, or bar, if it's categorical. And then I'm using this lapply that it's basically a list comparison in R. And I'm saving this in a vector. So this is going to be a vector that each term or each element is going to be one plot. And then I'm going to be using this plot grid to plot all those distributions together. So that's how we do that. And we created this nice grid plot. And even the labels here, auto, is going to show here A, B, C, D for you. I'm just saying what's the number of rows and columns. You can change that, or it's going to calculate for you automatically. And what you're observing here is that none of those distributions are normal distributions. So that would be nice if you did some transformation, probably taking the logarithms or the square root and try to remove any nonlinear nonlinearity on those kind of distributions. And for our target, we see that you have a high amount of zeros, actually. So we have a data that's highly populated by zeros, and also highly populated, not as zeros, but not the same as zeros, but highly populated as ones, and some numbers between. So now we're going to be going for the modeling. So first, we're going to do our modeling considering all the features, even the remaining oil height and remaining gas height. And see how we do. So here, I'm just getting the names. So I'm just getting the numerical column list. I'm removing the target and adding the send, because I want to use the send as well as a target. But remember, send is a character. You're going to need to keep it as categorical, but we need to make it numeric. The model doesn't understand character data. And here we are just saying what is our target. So to do that for the send, I'm just saving the table or our data frame to a new data frame just to not overwrite. And now we're going to say the send column is going to be the numeric of the factors of the send. So when you get to the factor, we are converting them to numbers. That's what we have in here. If you just run this, let me just run this first. And if you run this selection, that's what we have. We have those characters. Those are the name of the sends. Now, if you run the factors, so we created in a level the numbers. So we have 20 different levels now, and they are ordered and they have numbers now assigned to it, but they are still not shown. But when you converted these as factors to as numeric, now we have them converted to numbers. So that's just for us to run the machine learning model, the gradient boosting. And now our send, that might be the last one. Now it's numeric. So that is a question. How did you decide to perform the EDA and modeling R instead of Python? Well, that's an interesting question. It's because I personally am more comfortable with R, and I really like the libraries that they have for this type of data analysis. Remember that R was created from statisticians to use for statistics. So they do all this type of data analysis and statistical analysis, and we have a huge amount of libraries to do that. And remember that every person that creates some type of analysis, they can create a library and make available in CRAN. That's the repository of R. So we can find different ways and different types of plots and different types of analysis very easily in R. So, but that's my preference. Probably you can do the same in Python. But I have a high preference for R in this case.
Marcelo, just a quick question. When you select part of the code, what key do you use to run that particular part?
Oh, yeah, Control Enter.
Okay, thank you.
If I just select, do Control Enter, or if only the row, if I just want to run this line, Control Enter. I just go to this line. I'm not selecting, Control Enter. I just run the line. If I do Control Shift Enter, I run the whole chunk.
All right, thank you.
Okay. So now we're going to start to do the separation in train and test. And that's what I'm going to be doing. So we know that we have 400 wells, and we created that well ID that go from 1 to 400. And I'm going to be separating 20% of those wells to be our validation well. So basically, those are 80 wells. What I'm doing here, I'm just creating a sample from 1 to 400 and randomly getting 80 numbers from there. So there is a question asking if S factors is equivalent to one hot encoding in Python. I don't think so. I think those S factors, we are just giving a numeric order to your classes. But I think one hot encoding, you create new columns for each one of those classes and put 1 or 0, right? Those S factors is going to be saved inside the data frame, but it's not creating new columns. It's just giving that that column has also this information. Those numbers are called levels. So that for the send names that had those character name, so it had those levels that goes from 1 to any other number, to the maximum number that you have there. Would be equivalent to label encoding in Python. Yeah. So here, just going back to the code, we have this sample. So what you're doing here, we are just getting numbers from 1 to 400 and randomly selecting 80 numbers from here. So I'm going to be sorting. So they go from the smaller to the largest number. And here I just set a seed. So all those numbers come from some kind of a random seed. And we are just saying that the random that you're going to be getting, it's always the same. And then those are going to be the well names or the well IDs that we did to be our test wells. So here, we're just going to be separating what is for the train. So we're going to be using this pipe and this function filter that come from the Plotly. And those functions are very nice because they are simulating the way that you do data selection in SQL. And they're just selecting what is not in well test is going to be for train, and what is in well test is going to be for the test data. So when you run these, you're just creating those 2 new data frames. And here we just want to make sure that the well tests are correctly picked. So we want to see that if any of the well test names is inside the train well ID. So you see that they are all falses because we don't have any of the testing wells in the train well ID. But we have all truths because all of them are inside the train well ID. And that's how we start to do the modeling. There are actually 2 ways to do the modeling in Tidymodels. So if you go to the Tidymodels website, I like to show this. So Tidymodels, it's basically a wrap-up of different other libraries in R related to data modeling. We have the R sample to do the data split, recipes that's that's to do workflows. The parsnip is the machine learning. So when you are using those type of functions, so yeah, I see a comment here that just wanted to mention that there is a package called rsample to do the splitting into train stat, little easier. I know, but the type of splitting that I want to do here, I want to leave one wells out, not rows out. Remember that I have this is, you can understand this as a time series data. We have different dates. So I don't want to remove just one date of one sand. I want to remove the whole well for the test. So that's why I'm not using this rsample, because that would be removing the rows randomly. I want to remove wells randomly. So the parsnip is the machine learning, the one that you're going to be using. The tune is for grid search, and I think Yardstick it's also for grid search. So we have those packages that come inside here. All those packages are, oh, sorry, the Yardstick is for the metrics.
So Marcelo, can you remove a percentage of the data too? Sometimes they just take a percentage out as a blind test.
Yeah, you can do that, and that's the comment that they said here, that you could use the rsample and just remove 20% of the data.
Yeah,
it's gonna be. You could do that, but I don't want to do that because we have correlation between the holes.
Right, and also if you remove a single well, you can look at how well it's been reconstructed, right?
Exactly. So
yeah.
I'm using what they call the leave one out.
Yeah.
That's the methodology.
Blind prediction.
So here are going to be using the parsnip. And if you click here, they have the installation, but let's go look at the reference. And those are all the models that you can be using. The boosted trees, that's for gradient boosting, decision tree, logistic regression, linear regression. They have this neural network for MLP. They have Mars. This is very interesting to do also forecasting. They have supported vector machining, random forest, and all these models that you can run in here. And it has a very nice advantage because you can also select from which sub-library that you want to run. I'm going to show this later. So that's how we're going to be running this. So we're going to select our function, that's the boost tree in here. And if you don't select what's the engine, it's going to be running XGBoosting in the background. So when you install the Tidymodels, all those machine learning libraries are going to be installed in the background. We just have to say what is the mode. I'm saying the regression. The number of trees means the number of iterations that you want. The max depth. And we want to do our early stop, means that if after 50 iterations, your metric is not getting better, it's going to stop. And then we do a learning rate of 0.01. And you can just do the pipe and fit the data. So when you just run this, we just create the object that is a model, but it's not trained yet. And it says what is your engine. So it's the XGBoosting in this case, and the parameters that you select. If you want to fit this, you have to do this fit. There are the fit or the fit XY. The fit XY makes it very similar to the scikit-learn, where you select what is your axis. That's going to be our train and features. So just selecting all in the train data set, what are the features, and our Y, that's our target, is going to be just the target. So if you run this, so our model is going to start to train. So it's going to take a few seconds just to train. But there are different ways that you can do the same type of modeling. Instead of to use this fit XY, you can use a formula. And instead of fit XY, you use the fit and you define a formula. And this formula, it's very powerful, and I'm going to explain in a few seconds. So it's just going to get a little bit slow. Usually that happens when I'm sharing my screen in Zoom. But when I'm not sharing, this should run in a few seconds. So do you have any questions so far? Any comments? You can type your questions in here. Okay, so it finished to run the training. So we're not going to be doing the cross-validation, but also there is a library for cross-validation inside these Tidymodels. So I believe that you have one. I think you can do these both in recipes or workflows as well. But yes, there is a way to do cross-validation inside those Tidymodels. We are just not going to be going through that today in here. So you use all the features in the dataset. Yes, I'm using all the features. I'm not doing a feature selection. Actually, I'm not using the date feature. I'm just using the time difference between the surveys. Or am I using date? I believe I'm using date, right? No, I'm not using date. Remember, I'm just using the numerical columns to do the predictions. So the date is not one of the columns for the prediction. Is there a reason why I'm using a boosting algorithm? Well, I'm using actually a tree-based method because that's an easy way to work with numerical and categorical features. Remember that descent is a categorical feature. If you want to do regression, that's what we are doing here. Using categorical features, there are some extra steps that we're not going here today. But the tree-based methods, they are very simple. As we are doing just a bunch of if conditions, so it doesn't matter if they're numerical or if they are categorical. So now that we run the model, so those are our RMSC for all the runs, and here all the information from what we ran. So those are the number of features, number of iterations. We got to the 1,000 iterations, so it was always decreasing the RMSC. So the root square of the mean squared error. And this is the best training RMSC. Here, what I was going to say that you're going to be creating a formula. So we have to create a formula. And that's how you build a formula. So I'm just going to convert our features to formula. So I'm just going to show what is this output. And what is this F? So we created this formula. We are saying that you're going to run this model where our target is going to be in function of all those other features. So that's why I have this plus. This plus means that each one of those features, they are independent. And it's quite powerful to use formula because you can use other symbols. You could use the symbol for multiplication, that's the asterisks, that is actually going to give the combinations between of those parts in here. So it would be these independent, and the multiplication between both. So you could save memory by doing that. Instead of to create features or create new columns that are the multiplication or the combination between them, you can do this during the modeling. And that's very interesting way to use. Okay, someone asking if the boost method performing better without the missing data. If so, what would be the best way to fill in the missing data? That's actually a hard question, but in general, every model performs better when you don't have missing. If you have complete data, it's gonna work better because you have the information from all the columns and all the features that you can have. And what is the best way to fill the missing data? That's a tricky question. Actually, to do data imputation, it's a whole field in statistics. There are different ways to do that. There are a few videos that we did in the past that we completed missing well logs using regression, using the other columns, the other well logs. But you can do different methodologies. Depends of the data that we have, you have to choose a different way. So there is not a best way to do. That is the way that's more, that fits better your data. Now we just have this formula. So you meant for this data set. Again, we are not working with missing data for this one, so we don't have what would be the best way. That would be a trick question. So that would be a paper by itself. So I cannot answer this now. So here, now you're just gonna train the model. So now we have this formula where our target is in function of the others. And I just included these parts just to see how you can select the different engines. So here I'm just selecting the XBoosting again. And also you can select the mode outside the boosted tree. I'm just saying that set the mode as regression. And here I'm just gonna fit now this model. So usually somehow when you do this in formula also runs faster. I said that you can select different engines, but how do you know what are the engines for each one of those functions? So the engines means different libraries that you can use. And Tidymodels and the parsnip, in this case, can do boosted trees with from three different libraries, can do MLP from different libraries as well. It uses Keras, it uses and net and others. So this is how we train the data. So I also run the 1000 trees and just got a little smaller RMSE, but technically that's the same result. And here the engines that can select from this. So you could use to set your engine and the modes. You could use the XGBoosting that used for classification and regression. The C5.0 is just for classification. You can use Spark, that's for classification and regression. If you're using, for example, the MLP, you can use Keras or NNet. If you're using Mars, for example, it's just one library, that's the library Earth. And random forest. So you can use the libraries Ranger, random forest, and Sparks, and both are for classification and regression. So those are different libraries. They have different algorithms and different advantages and disadvantages. So you select what you want to use. Here, I'm just calculating the results now that you have the training model and saving a table. And here I'm just fixing that everything that's lower than 0 to be 0, everything that's higher than 1 to be 1, because you cannot have negative numbers or numbers higher than 1. But a regression model will give these numbers. So when you run these, those are our predictions compared to the true values. Just by looking at here, looks like you're doing a very nice job. Then those are some metrics. This is from the library's yardstick. So the RMSE, the R squared, the mean absolute error. So the R squared one means that you have a perfect prediction. So you have something close to perfection in here. Here, it's how you can use Python inside R. I just included these because I want to show how to do that. So I want to use for one of the metrics, the explained variance score. That's a good metric for regression. And we use this function import from the reticulate and the library and the model. So scikit-learn, sklearn.metrics. And I'm saving here in this object. That's actually now a scikit-learn object. And inside here, I select which function I want to use. I want to use the explained variance score, and I do how you do in Python. You put the original, the true, and the prediction. So when you run, it takes just a couple seconds to upload your library in Python, from Python. And it's very important that your R Studio needs to find where is your Python installation. To do that, you come here to the tools on the top, then you go to the global options, and you might have here on the left the Python, and you set where is your Python installation. So here, the explained variance score, that's a number that goes up to 1, and 1 is perfect, means that you're having a very good prediction. So when you do the cross plot between the true and the predictions, we see that most of them are actually falling over this diagonal line. Let me just make this figure a little bit small. So they are basically doing a very good prediction. We have some outliers, but the predictions apparently are doing very okay. And if you plot our feature importance from the library VIP, that's what we have. So those are the importance. So as we saw from the correlation plot, remember that I told you that the gas height that had a correlation of 0.9 on the experiment, and this one had a 0.66. So you're saying you're expecting those two to be the most important features and the gas height to be the most important feature. And that's what we had. And all the other features, basically, they have no importance in comparison. So I submitted with this one. I got a so the question is, can you predict for the test and submit? Curious to see the RMSE. I submitted this one before just to see. The RMSE was very low. It was a very good prediction, but now they deleted the scoreboard and removed these two variables. And then I'm going to show you what happened if you remove those two variables without doing any pre-processing. So that means that we can do the predictions using only those two features. Okay, so then I got really annoyed with these results when I got this the first time. And then I talked with David Emery, that he's a specialist on this type of data, because when you get predictions that are good like that, they are too good to be true. And in my experience, means that something is wrong if you have that perfect prediction. And then talked with David, we realized that those two features, they are actually calculated from the target. So this is called a leakage. So we already have somehow the answer in here. So what I did was just to run everything again. removing those two features. So now now I can run everything again and not using those two features. And let's do the same run with all those two features. So I'm just going to create now in the features. I don't have them anymore. I'm just going to recreate all the tables, split the data. Then I'm going to run the predictions. I'm going to fit the model. So I'm going to do this in equation because it's a little bit faster. Also 1,000 trees, the max depth of 8 is going to stop after 50 iterations, and the learning rate is 0.01, XGBoosting, regression, and our function is going to be our targeting function of all the other features without any type of correlation between the features. So we ran. Now you can see that our RMSE is not getting so low as before for the training data. We still run 1,000 iterations. And here, now you're going to see the predictions. And then you can start seeing the numbers. So those are the predictions. From these first ones, we can see that they are not doing that great. But when we start going, we can see that what's supposed to be 0, we are predicting numbers that are not 0. And you can see the bunch of zeros are not being predicted as zeros. So we're actually getting very high numbers where it should be 0. When we see our metrics, remember those numbers, the R-square very close to 1. Now we just run these. So it got a 0.14. That's a very low R-square. And even our explained variance score that was almost perfect got to 0.1. And if you do these cross plots, we are expecting a diagonal. So basically, we have our model, just the simple model without working with the data. We can't do any predictions, basically. And when we do our feature importance now, so it's going to be different. So what happened is that we didn't work the data set before. So remember in the beginning that you don't have normal distributions of any one of those features. And it's recommended to do some kind of a transformation. So we didn't do this transformation. So that's still going to be a future work in Cruise. And those are the feature importance. Remember that I told you that the total injection was the feature with the higher correlation besides the remaining oil height and remaining gas height. So basically, that's what I'd like to present today. So those are interesting ways that you have to see, and we have always to look at your data when you're doing a machine learning project. You have to understand your features. So you avoid that saying that people like to say garbage in, garbage out. That's going to happen, but only if you let garbage in. So you have to understand your data, and you have to work your data to not be a garbage. So remember, you're going to expend 80% to 90% of your time just working with your data before doing any modeling. If you just go for modeling without thinking of the data, you might get those kind of bad results that you're getting here. So that's what we had to present for today. I'd like to thank everybody for joining us, and stay tuned for the next session. Thank you, and see you in 2 weeks.